So we're going to have a short section here on the eye. Excuse me. That's an eyeball. I'm going to give you a physicist version of an eye. So this piece here, the curved piece that sits on top of your eye, is called your cornea. You have a lens back here, and the shape of this lens is adjusted by muscles. Maybe I'll draw the muscles in red. They go all the way around the eye, and they make this lens thicker or thinner. Somewhere in here is your iris, which has an opening in it to let the light through. So this is the iris. Doesn't leave the eyeball. So that's the iris. This fluid in here is called the vitreous humor. Back along this back wall here is the retina. Straight back from the center is where you have the highest density of light sensors. This is called the fovea. It's better at color sensing than light dark. Out here is the optic nerve coming out this way. What's interesting about the eye is that it's got a fixed image distance. In your book they call it d sub I. We call it s prime. But anyway, the image distance is about 2 centimeters for every eye. It varies a little bit, but basically this lens has to create an image on the retina. It can't be behind it or in front of it. It has to be on the retina. And so the image distance is always fixed at 2 centimeters. We'll assume it's that way for every eye, even though we know that there's some variation. Obviously, this is a complicated optical system, but we kind of just treat it as a single lens. And so if we wanted to write an equation for this, we'd say, 1 over the focal length is just 1 over s plus 1 over s prime. Clearly, if I have an object near my eye, an object distance that's small, then I need a larger focal length, because this guy doesn't change. If s gets small, this number gets big, and that means I have to have a smaller focal length to make this side bigger, so that I can accommodate these a nearby object and a 2 centimeter image distance. When we were working in lab, we had a fixed focal length lens, and if we moved the object, we had to move the position of the device that you projected the image onto to accommodate that change in distance. What your eyeball does is it just adjusts the focal length to keep putting objects at different distances at the same image position. And so it turns out, so this guy is always 2 centimeters, the image position. Humans have a near point of about 8 inches. It varies a little from person to person, but it's close enough, 0.25 meters, that we'll just assume it's the same way for everybody, just like that 2 centimeters. So this is the closest or a typical person can focus. People who are very nearsighted can focus more closely than this, but for a normal eye, that's about it. And so we can say, look, we can say at the near point, when an object is at the near point, it's 25 centimeters away. That's the closest I can focus. This is going to be the most converging my eye has to be because it's trying to converge rays for an object that's really close to my eye, and so those rays are spreading out very rapidly, unlike if it was really far away where they would be coming in mostly parallel. And so so the focal length I need for that is 1 over the object distance plus 1 over the image distance, which is 1 over f is equal to 54 over a meter, and so that gives me f is equal to 1 over that, so it's 0.0185 meters. So for the near point, is 1.85 centimeters. That's the shortest focal length my eye can make and still bring an object into focus. And so we can ask the same question about the far point. This one's a little easier to do. We can see objects that are very far away. I mean, if they're big enough for us to see, we can focus on them. And in fact, our eye is relaxed when we're looking at infinity. That's why, like, microscopes and telescopes will generally put the image distance at infinity when you look through them, so that your eye can just relax and doesn't need to accommodate the object. Our eyes are straining when we're trying to see things that are nearby and relaxed when we're looking at infinity. And so we can say, look, in this case, 1 over f for an object that's infinitely far away, 1 over s plus 1 over s prime, which is 1 over infinity, plus, again, the image distance doesn't change, again, 1 over 0.02 is 50, and so that means that the focal length is 0.02 meters, which is 2 centimeters. And so actually the total range of focal length isn't that big for my eye. It varies between a 2 centimeter focal length and about a 1.85 centimeter focal length for the nearest objects I can see. And interestingly enough, as we get older, our eye really loses its ability to do this. As you get older, you pretty much stuck at this, and so that's why we need reading glasses and stuff to accommodate the fact that we want to see objects that are nearby. People who are in their 60s might have a near point of a meter or something like that. Your arms, you have to hold something at arm's length before your eyes can focus it. That's a little bit about the eye. So we're going to do problems with the eye issues, right? One of them is nearsightedness. A person who's nearsighted, so let me draw an eye over here somehow, right? So if you have an eye that's nearsighted, what it's basically doing is if the object is far away, the lens is too converging, and so it causes the rays to focus the image too close, not on the retina, too close. And so the way you correct that is you put a converging lens in here, a diverging lens in here, and that spreads the rays out a little bit, and that makes it harder for the lens to focus them, and so they end up getting focused back at the eyepiece, back at the retina. And sort of that's how you correct it. And so the way we draw this, let me just draw this a little better here. And so here's my eye, right? And here's my lens. I'm just going to draw it as a lens, right? And what I do is I need a diverging lens for nearsightedness. And so this lens is held on by glasses, and we estimate this distance is about 1.5 centimeters, how far away the glasses are from the eye. What you want to do with this lens is take an object that's at infinity. So here's my object that's at infinity, and I want to make it appear as though it's 30 centimeters from the eye, or 28.5 centimeters from the lens that I've got, right? And so I want to take an object that's in infinity and make it an image at 28.5 to the left of my lens. And so I can just grab my formula. This is the focal length for this guy is 1 over s plus 1 over s prime. The object distance is infinity, so it's just 1 over infinity meters plus 1 over. And so I want my image to be at 30 centimeters from the eye, or 28.5 centimeters. But it's going to be to the left. It's going to be on the opposite side of the outgoing ray, and so it's going to be negative. And so if I evaluate this, I get my focal length is minus 0.285 meters. If I want to convert that into a power, it's about 3.5 diopters minus. The minus sign makes it a diverging lens. Nearsighted people need diverging lenses. But the philosophy is you take an object that's an infinity that the eye can't see because the rays converge too much, and you make it appear as though it's at the far point of the eye, which is 30 centimeters, and that corrects the problem. So let's talk farsightedness now. Suppose my near point is 1.0 meters. I want a lens that will make an object at 0.25 meters. Take an object at 0.25 meters at a normal near point, like I'm reading a book or something, right, in front of my face, at 0.25 meters, and put an image at 1 meter, because this is the position where my eye can see. And so it's the same picture I had a minute ago, right? Here's my eye, here's the lens, right? Here I have an object that's 25 centimeters from my eye, or, this distance is 23.5 centimeters. And I want to make it produce an image that's back here at 1.0 meters, or this distance is 98.5 centimeters. So this lens, which is again 1.5 centimeters from my eye, because it's on glasses frames, my eye can only focus as close as this, and so I want to take something that's near me and create an image of it back here so that my eye can can see this thing, right? And so once again, for the lens, I get 1 over the focal length is equal to 1 over the object distance, which is 1 over 0.235 meters, right? Plus 1 over the image distance, which is 1 over, again, this is on the opposite the outgoing side of the ray, right? The ray goes this way, and so this is going to be a negative distance for this guy. This is going to have a negative image distance of minus 0.985 meters, and so this is going to give me a hang on a second, I just got to do a quick calculation. Sorry, that's the 0. So, sorry, 1 over the focal length. 1 over the focal length is 1 over the object position. Again, it's relative to my lens, because my lens is the thing that's going to create an image where my eye can see it at a meter. And so 1 over the object distance plus 1 over the image distance. Again, the image is on the left, is on the opposite side of the outgoing ray, and so that gives me minus 0.985, again, because it's not at a meter, but it's the distance from this lens, which is 98.5 centimeters. And so if I evaluate these two, I get 4.255 over 1.015. And so 1 over f is equal to this. That's actually the power. So I could say the power is 3.24 diopters, right? That's the same thing as per meter. Or the focal length. Notice this is a positive focal length lens. It's a converging lens. And the other one, in the nearsighted example, it was a diverging lens.